Okay, Chemistry 2341. We're going to continue on with Chapter 7, Part 4. We're going to look at the alkyl halides and the E1 elimination reaction. Okay, so when we talk about the E1 reaction, we need to first think about the idea that it is regioselective. Like E2 reactions, the major product is typically the more substituted alkene, and therefore Zaitsev rule applies. Okay. Now, it does go through a different mechanism than the E2 reactions, but the rule tends to apply, okay? So if we think about this reaction here we have the 2-chloro-2-methylbutane, we have the possibility of it reacting with these hydrogens here or these hydrogens, or the possibility of reacting with these two hydrogens. Even though these are the 6 equivalent hydrogens there, these two hydrogens give the more substituted product, therefore they are the major product right here. So our major product is the tri-substituted alkene as opposed to the di-substituted alkene here, okay? So within the same alkyl group, the relative reactivities are based on the leaving group ability. So the weaker the base, the better. So iodine, HI is the strongest acid, therefore it's the weakest base. HF is the weakest acid, therefore the strongest base, means that iodine is going to leave first, followed by bromine, chlorine, and fluorine, okay? So because it's an E1 reaction, the leaving group leaves first, therefore its relative reactivity is driven by the leaving group leaving, okay? So let's talk about that a little bit more. Because we're forming a carbocation, that means that the increasing stability of the carbocation is what drives the rate of the reactivity. So if we have a tertiary alkyl halide, it's going to go much, much faster than if we have a methyl or a primary, okay? So in these cases here where we have methyl and primary, you're more likely to start thinking about, substitution reactions than this E1 elimination. But the faster it goes, the more likely it is to be a tertiary. Again, it follows carbocation stability. So let's talk about that. Since we are forming that carbocation intermediate, we have to think of possibilities of forming 1,2 hydride shifts and 1,2 methyl shifts. Now, in addition to getting Zaitsev's rule to get us the most substituted alkene possible, we also want to think about getting conjugation or double bonds in resonance. So in both of these examples, we're looking at Zaitsev's rule as well as what's more conjugated. So in the case of this bromine right here, this is on a secondary carbon, okay? Now, so we're going to have bromine leave and give us our carbocation. We can then do a 1,2 hydride shift to allow the positive charge to go over one carbon to be in conjugation with the already formed double bond. And then that'll allow enough time for the base to come in, eliminate hydrogen, and give us our conjugated heptadiene. In the case of our benzylic material, obviously we have a secondary carbocation here. It can form a tertiary carbocation by doing a 1,2 methyl shift to give us our benzylic cation here. The benzylic cation is one of the more stable cations. It's even more stable than the tertiary. So that means it's going to do that 1,2 methyl shift and give us our tetrasubstituted alkene as opposed to our di-substituted alkene, our monosubstituted alkene that would be if we just eliminated across this section here. So that 1,2 methyl shift gave us a tetrasubstituted alkene. Okay, so why is there stereoselectivity in these, the E1 reactions? Well, the first thing we have to think about is the fact that we, number one, form a carbocation. So that's the first step that happens, okay? So that once we get that carbocation to happen, we get to this trigonal planar system so that we can get attack from the top or bottom, or elimination of this hydrogen from the top or the bottom. So what we're thinking about here is trying to rotate the system such that we have the two largest groups farthest away from each other. when we do that, we end up with the E isomer as our major product. Again, we're looking at getting those two groups as far apart as possible. And so when we rearrange this carbocation, when we rearrange this carbocation to figure out which one of these groups is furthest away, we're going to get this is our largest group here. Oh, this is our largest group here. And on this side, this is our largest group here. So we're going to get those opposite each other, and we're going to end up with our E product here as our major product with the two largest groups farthest apart, as opposed to our minor product, the Z product, with our two largest groups together. Okay, so it's all about trying to form our more stable alkene. So even if you're remembering the Zaitsev's rule and getting the more substituted alkene, you also want to get the trans alkene or the E alkene, because that is also more stable. Okay, so unlike in the reaction of cyclohexanes, when we did the E2 reaction, where we were looking at a specificity between the equatorial versus the axial hydrogen, because we're going to this trigonal planar intermediate, we don't need to worry about that anymore. All we need to do is follow our Zaitsev's rule and get the most substituted alkene possible. However, don't forget, because we have a carbocation, we can still do a 1,2 hydride shift to get that Zaitsev's rule product. So for example, here on the bottom, we have a possibility of the bromine is here on the secondary carbon, but once we form that carbocation, it can rearrange to give us our carbocation here, which actually ends up giving us our tetrasubstituted alkene. In the case if it did not move, it would give us our trisubstituted alkene. So we still have that 1,2 hydride shift because of the stability of the system. And again, we're moving through this trigonal planar system, so it doesn't matter whether this hydrogen is equatorial or axial when it leaves. It really doesn't matter, and we can always try to form our Zaitsev rule apply. Okay. So in summary, because all it depends upon is the alkyl halide, we have a first order reaction. The reaction happens in two steps. We form our carbocation intermediate, and then we form our second transition state and our product here. So this transition state is when our halide is leaving the group and taking away its electron. This transition state is where the base is removing the hydrogen, and those electrons between the hydrogen and the carbon are coming in to form our double bond. Because we're forming the carbocation intermediate, tertiaries are faster than secondaries or faster than primaries. Now, the reason this reaction works through that carbocation intermediate is because we have very weak bases like waters and alcohols. It's favored because instead of acting as a nucleophile, it's waiting for the leaving group to leave to form that carbocation, and then it can come in and do the reaction. That means the leaving group drives the reaction here. Therefore, iodine is faster than chlorine. Iodine is faster than bromine, which is faster than chlorine, which is faster than, okay? Now, because weak bases like this water and alcohol are favored, that means our protic solvents solvate both the cation and the anion intermediates. Therefore, protic solvents help the reaction go. So in total summary, E1 is regioselective and stereoselective because it always follows the Zaitsev's rule. It does compete with SN1 because you can have the base come in as a nucleophile, given the opportunity. It will undergo rearrangements, and therefore E1 reactions are much less useful than E2 reactions because of the possibility of rearrangement, the 1,2 hydride shift, and the 1,2 methyl shift. We could have a bunch of different products available to us, which is why having the base come in and start tugging on that hydrogen first, and so you only eliminate in the specific location, makes it the E2 reaction a little more useful. Okay,